دقيقة. تمام. حاليا بدأنا نعمل ريكوردينج. اوكي تمام، نجرب الريكوردينج. طيب اول ما نفتح البرنامج انا بس خليني نعمل لنا برزنتيشن صغير كده عن البرنامج ده. كويس. الو الو.
ايوه اوكي يس I'm hearing. سامعك كويس هذيك.
سامعني انت؟ طيب تخليه قبل كده كان عرضت عليكم.
ايوه كان في الجامعة تقريبا اول سمستر.
اي كان كلامنا عنه، بس انا عامل ايه جنب للحته دي اللي هي الفيزيكس حقت الفلو. الفيزيكس حقت الفلو من ناحيه بتاعت from time point of view. ما اعرف شرف لسه ما خش. طيب from physics point of view نحن عاملين ريكورد ممكن بعدين نشوف الريكورد. طيب uh, from time point of view the flow either be steady flow or unsteady flow. الو
ايوه يس.
سامعني يعني؟
يس صوت واضح.
طيب يا شباب شباب سامعني كويس؟
ايوه الصوت واضح.
طيب تمام. I would like to okay. Okay. Okay, Sharaf, I will start from this presentation. Actually, this presentation is a basic presentation. So,
Doctor, the screen is not sharing. I think there is some problem with it.
really?
Yes, it was there, but now,
Okay, what about now?
yes, now, sure.
Okay. In this content, we are going to view some basic for the CFD analysis. The content of this presentation would be an introduction to CFD and why we need the CFD and the role of CFD in the design process. Actually, I will jump directly into physics and tree analysis and for the geometry modeling, computational domain, the boundary conditions, the meshing or grid generation, and we would like finally to speak about the successful steps for the setup of the problem in Fluent and types of Fluent. We This is the common definition for the CFD. It is applied for fluid flow and heat transfer as well as for the chemical reaction. And you well know about this. Some solutions that now came with CFD in previous was problem like يعني in a report for NACA 821 report, we state that the shock shape and detachment distance cannot at present be theoretically predicted. But in 2013, these guys from China, they make a review for the shockwave detection method, and they will show the distance for the shock detachment. So what was impossible previously now became possible with CFD. And this is what is CFD, and mashallah, we will know about this. Uh, we know that for the fluid dynamics, either we solve the problem experimentally or theoretically or computation. So CFD combines both efforts from theoretical and mathematical modeling and also for the experimental that some solutions are يعني modeled or uh, solved from experimental basis for the validation so CFD is complementary for the theories and internal experiment. So this is the advantage of CFD. The process of successful CFD simulation of problem that we have a pre-processing uh, stage and we have a solution stage and we have a post-processing stage. When we say pre-processing, then we mean the creation of the geometry, the next generation, and once we define the grid or we design the grid, so by default we already define the computational domain. Okay, are you getting my voice clearly?
Yes, but we'd like you to actually increase your volume a bit. If I hear you
Okay,
better.
okay. A minute. Okay. Now it's better. Hello.
Yes,
Now it's better. Are you
yes, now it's there.
okay? So
Yes, it's better. We can hear you.
for the pre-processing, yes, the volume was a little bit low. The pre-processing it means that the creation of the geometry and the mesh generation. Once we generate the mesh, we define the domain, the computed domain, which is called the computational domain. This is the pre-processing. For the solution, there is like the equations that we are going to solve, and besides this equation that we are going to solve, because there will be a closure problem. The number of unknowns is greater than the number of the equation for the solution. So we need a closure for this problem using a physical model. For example, we have a turbulence models, we have a combustion model, we have a radiation model. So by this way, we can uh, define a set of equations that the number of unknowns is close to the number of the equations or the degree of freedom. So the problem will be deterministic, not undetermined matrix. We know from the numerical method that for the matrices, the solution should be determinant when the matrix is square matrix. So if the number of unknown is equal to the number of equation, in this case we have a deterministic matrix here. For the solver setting, we have the initial boundary condition, the solution control, and we have the monitoring control. After the solution stage, we have the post-processing stage. Here we gather the solution, we gather the results either in XY plots, for example, the boundary layer, velocity profile, or such like that. And also we can define contours or vectors or pathline. So we have a post-processing problem. ANSYS is a complete set solution. So you can define the geometry, the mesh generation, the solution, and also the post-processing. So in this case, for example, this is the user interface. This is the graphic user interface for ANSYS. And when I open, there will be an analysis system. This is a complete set solution for each problem. Our problem, because ANSYS is a very big program with a lot of solutions, affordable or provided from electric, from structure to thermal to fluid. So there are a lot of physics, multi-physics program. We only we are focusing on this one. We don't care. We don't need the others. We only need the fluid flow using fluid. Okay. Are you seeing this screen now for ANSYS workbench?
Yes.
Okay. So we will either we drag it to the project schematic. There is here. This is a project schematic. So you can design your project. Okay. So either I can drag it like this way. In this case, I have a complete solution, a complete set of the solution from the geometry to the grid to the setup and solution to the results. So these two phases are the pre-processing, and these two phases are the processing, and this is the post-processing phase. Okay. For the geometry, ANSYS has two software, either Space Claim or Design Modeler. Actually, Space Claim is close to SolidWorks, and Design Modeler is close to CATIA. So if you know SolidWorks, you can use Space Claim very easy. And if you know CATIA, you can use Design Modeler very easy. For me personally, I train myself in design modular more than space claim. But you can train yourself also in space claim. So you can use يعني you can use both of them يعني. And they are very easy. You can model the basic geometry here. But if you have complex geometry like, for example, our problem for the Hyperloop or the problem for Sayyid Ahmed for uh, the wind turbine, it's better that you model your problem in SolidWorks or in other CAD environment, okay, and then you import your case into يعني into ANSYS using يعني import geometry method. In import geometry, you can browse for extension, for example, step file or IGS file or SolidWorks file or CATIA file. Model, the model for the CAD model. Okay. But in this case, for example, we can begin with a very simple tutorial for يعني for the purpose of يعني identifying the different graphical interface for ANSYS. So we can begin by simple 2D problem that, for example, flow over flat plate or flow around as a symmetrical pipeline. Okay, so we will start the design modular. I will share with you a step-by-step tutorial. Okay, you can go through this tutorial. Okay, this tutorial for a laminar flow and validation of turbulent pipe flows. So we have the geometry, we have the physics, we have the mesh generation or grid generation, the solution and results. Since that we have a laminar flow and we have a turbulent flow, so يعني the physics are different. So maybe the grid also will affect by by the physics of the flow. So for example, if we have inviscid solution, since it is inviscid solution, so there is no need for for يعني increasing the number of elements near to the wall because it is inviscid solution. But if we have a viscous solution, then here we have to consider to increase the number of elements near uh, to the to the wall. And if the flow is turbulent, we have to consider this much more than the, the laminar case. Okay, uh, and in this for this problem, uh, there is the so-called Y plus definition. The Y plus is a non-dimensional unit that correlate between the flow velocity and the farthest layer of the grid near to the wall, the distance delta y. Uh, distance between this parameter the y plus when it is much less, this means that you model your boundary layer much better. Inside the boundary layer, let me share a whiteboard with you now. If this is y, okay, and if this is u, near to the wall, this is our wall, okay, this is our wall. So the velocity profile will become like this. Near to the wall, the velocity is 0, and when we reach his delta, u equal 0.99 of u h. Is that okay with you? Okay, and we have the velocity profile by this case. Inside the boundary layer, we can divide our boundary layer into sublayer. So we have this region, and maybe we have this region also, and we have outer layer. The inner layer, this is called viscous sublayer. Okay, and then there is the so-called log layer. And then we have the outer layer. Okay, so if for example I will share with you another important. Wait a minute. Okay. Okay. This is the definition for the white plus, and here this is the viscous layer, and we have the log layer or the buffer zone, and we have a defect layer. So there is not only 3 layers. We have this intermediate change or interior interface between the viscous layer and the log layer. The log layer, there is the so-called universal law of war. It is a log law. So if we if we came to into yes, this is the the universal law of work that u plus, which is the non-dimensional velocity, is correlated with y plus according to constant called kappa, and this law is applied basically in the log layer. The log layer active between 30 to 500. In the viscous sublayer, we have the law here in this case, and we have u plus and y plus are يعني defined by this manner. So if we went into y plus and less than 5, in this case we are going to solve the viscous subline. But it is difficult computational. The computational cost will be very high. So most of the industrial application, they went to simulate from the log layer to this case. So for industrial application, for solution for y plus greater than 10, this would be preferable. And even this, it is difficult. It is somehow difficult because there is a calculator, y plus calculator, and from the definition of y plus, which is equal to y multiplied by u star over nu, where nu is the kinematic viscosity. So y is the first layer thickness. So as we increases the velocity, I think the law for y plus. Okay, anyway, we are running out of time. Okay, this is a point-wise approach or software for calculation of the y plus. For example, if our velocity is 50, and if our density is air density, and yeah, this is our length, and if we want y our y plus to be 1, we can compute the first layer thickness is 7 micron, 7 to 10 to minus 6, 7 to 10 to minus 6 meter. So this means that we have to to decrease the wall spacing, the first layer of the grid, it should be about 7 micron, which is very low. And if it increases, for example, if the velocity increases, this much decreases. And for example, if we want into supersonic flow, Mach number 2, this became 7 to 10 to minus 7. So, as you increase the velocity, the delta will become much less. So, for industrial application, we can go to 10 to 30, and if the velocity decreases, so we can go to like 0.02 millimeter, 0.2 millimeter, which is a reasonable distance that we can the first mesh cell of the wall يعني will be يعني in acceptable industrial application for the industrial application. Did you get my point? So the physics of the problem will directly يعني affect my grade in this case. Okay. Okay. Uh, we have different methods for CFD analysis. We have Laplace, which is the most simple, the potential, the panel method, and also we have Euler solution, which is inviscous solution. For the viscous solution, we have RANS, which is Reynolds Navier-Stokes models, and we have the DNS and large distribution. And I think Dr. Ibrahim can explain about this different. The different physics are يعني in time we have steady flow and unsteady flow. For viscous, we have viscous flow and inviscous flow. If it is viscous, there is laminar flow or rate number, and then we have the compressibility effect if the density is changing with the velocity or the pressure. So then the flow is compressible, and if the density is not changing, so the flow is incompressible. And also we have low real number and higher real number. Uh, from point of view of internal flow and external flow, this is for the domain. And if, if the fluid is single phase or multi-phase, the multi-phase this means there is a mix between different different fluids. Okay, for example, oil and water, or if we are going to simulate the sloshing of a fuel tank, we have air and the fuel inside the tank, and in this case, the complexity will go into the modeling of the surface station and other forces. And also we have the acoustic model. So this is uh, the graphical interface, and we are going to utilize fluid flow using Fluent. And since our training will begin with new design, the design model. Okay. When we double click the design modeler, we have an interface by this way. Okay. The interface, we have file, and we have create menu, we have concept menu, we have tools menu, we have units menu, we have view menu, and help menu. And in this bar, we have start over. This means that if you do any model, if you click on start over, you are going to lose everything that you do, and you will begin a new design or a new file. Here you can save your project or your work, and actually uh, the workbench based on HTML and also uh, the PHP, I mean web-based. It is a web-based program. So when you save, for example, your case, for example, if I am going to to save it here, to tutorial. Okay, remember this is tutorial one file. If we went into this file, okay, this is CFD tutorial. As you see, this is our ANSYS project, and we have files project. It is similar to the web page, and we have the design point, we have Fluent, and this is our design modular file, and there is session file and user file. So if you want to copy the file, you have to select both files to copy it. If you copy only this, it will not work because all of the mesh file and other things are stored in this. During your case, there would be a backup file if, for example, electricity gone or you have a backup. But I recommend that you save your work each step that you do. This is say export. If you want to export your file for IGS or step file or any other, and here you can take a snapshot, and most of the snapshots are saved in user files. Saved in user files here, all of your snapshots. Okay, and then here you can select a point or an edge or a face or a volume. Okay, by default, it's better to select an edge here, filter by edge. Here you can rotate and you can pan, move your. This is zoom to fit. If your model is very big, so then you can select zoom to fit. Okay, and here you can your view would be if it is ISO, or you can go here